Now let's talk about Chebychev's theorem. Chebychev was a Russian mathematician in the 19th century, and he had several major contributions. But to statistics specifically, the Chebychev theorem gives us a way to determine how much of our data will fall within a certain number of standard deviations away from the mean. So here's a picture of a histogram from a textbook, Blumen's Elementary Statistics. We have our mean here in the middle, and we have 2 standard deviations away from the mean on either side, or 3 standard deviations away from the mean. Chebychev's does not talk about 1 standard deviation, and when you see the formula, you may understand why. Chebychev's theorem tells us the proportion or percentage of values from any data set that falls within a certain number of standard deviations from the mean. So that proportion of values falling within k standard deviations from the mean will be at least 1 minus 1 over k squared, where k has to be greater than 1 and not necessarily an integer. Why not k equals 1? What happens when you plug 1 in for k in this formula? If you plug 1 in for k, you'll get 1 minus 1 over 1, which will give you 0. So the formula doesn't work unless k is bigger than 1. K could be 1.1 or 1.4 or something small, close to 1, but it cannot be 1. So looking back here at our graph, at least 75% will sit within 2 standard deviations of the data. And that is because if I plug in 2, so k equals 2, 1 minus 1 over k squared, 2 squared is 4, 1 minus 1/4 is 3/4, which is 75%. So that's how we get at least 75% of the data within 2 standard deviations of the mean. If we look at 3 standard deviations, I'll do it over here on the left, 1 minus 1 over k squared, we get 1 minus 1/9, which would be 8/9, and if I divide that on the calculator, I get 0.8 repeating forever, and we'll round that last decimal place, and that's how we get 88.89% within 3 standard deviations of the mean. Here's a nice little concise snapshot of Chebychev's theorem, and I'll put that snapshot off to the side in our notes section. And remember that this is at least, the proportion will be at least 1 minus 1 over k squared. So at least 75% is within 2 standard deviations of our mean. At least 88.89% is within 3 standard deviations of our mean, and so forth. And notice the farther out we get from our mean, the higher that percentage goes, which makes sense. There's only so far that we can go with our data. The important thing to also glean from Chebychev's theorem is that this works for any data set. You don't even need to know anything about the shape, the nature of the data. Chebychev works for everything. So let's look at an example. The heights of the adults in one town have a mean of 67.5 inches and a standard deviation of 3.4 inches. What can you conclude from Chebychev's theorem about the percentage of adults in the town whose heights are between 60.7 and 74.3 inches? Some things that we know, we have a mean of 67.5 inches and a standard deviation of 3.4 inches. And since they say heights of the adults in one town, let's make the town's population our data population. So I'm going to draw a number line to help us visualize it a little bit. We have 67.5 in the middle as the mean. And then if I add 3.4 to 67.5, I'll get 70.9. If I add it again, I'll get 74.3. If I go the other direction and I subtract 67.5 minus 3.4, I'll get 64.1. And if I subtract again, I'll get 60.7. Now, again, this is meant for us to visualize, to understand where this is coming from. our mean here in the middle, if I look at 74.3, this number is actually our mean plus 2 standard deviations. Similarly on the other side, 60.7 is our mean minus 2 standard deviations. So we're being asked, what's the percentage of adults whose heights are between 60.7 and 74.3 within 2 standard deviations? So within 2 standard deviations from the mean, that means k is 2. I can use our formula, 1 minus 1 over k squared, and I'll get 3/4 or 75%. And we would say at least 75% of adults in the town have heights between 60.7 inches and 74.3 inches. And that's the idea with Chebychev. To contrast, we have another rule called the empirical or the normal rule. The empirical rule is only used for normal or bell-shaped distributions, also why it's called the normal rule. And here we have no formula, we just have a list. So the percentage of values from a data set that fall within k standard deviations of the mean in a normal distribution is listed in the table. Within 1 standard deviation, there's 68% of the data. Within 2 standard deviations of the mean, there's 95% of the data. And within 3 standard deviations of the mean, there's 99.7% of the data in a normal distribution. And we can look at another similar histogram. Here we have that bell-shaped distribution again. And within 1 standard deviation of the mean, there's 68% of the data. Within 2 standard deviations of the mean, there's 95% of the data. And within 3 standard deviations of the mean, there's 99.7% of the data. Sometimes this is called the 68, 95, 99.7 rule to help remember those numbers. Let's write some of this down. So approximately 68% of normally distributed data fall within 1 standard deviation of the mean. Approximately 95% of normally distributed data fall within 2 standard deviations of the mean. And approximately 99.7% of normally distributed data fall within 3 standard deviations of the mean. So I'll also put that table over here for us. And now let's put it into practice. The systolic blood pressure of 18-year-old women is normally distributed with a mean of 120 millimeters of mercury and a standard deviation of 12 millimeters of mercury. What percentage of 18-year-old women have a systolic blood pressure between 96 and 144 millimeters of mercury? Let's grab some information. We have a mean and a standard deviation. We're also given that the data is normally distributed. This is very important. If we're going to use the empirical rule for normally distributed data, we have to make sure that we have normally distributed data. And then we're also asked what percentage have this blood pressure between 96 and 144. So we need to determine how many standard deviations away from the mean these numbers are. We can't have non-symmetric values here, so 96 is going to be the same number of standard deviations away from the mean that 144 is. So we could essentially just calculate 1, how far away is 96 from 120, but I'm going to draw that number line again to help us with that visualization. So we'll start out with 120 in the middle. Here's our mean, and if we add 12, which is our standard deviation, we get 132. And if we add 12 again, we get 144. So 144 is the mean plus 2 standard deviations. If I go backwards and I subtract 12 from 120, I get 108. And if I subtract 12 again, I get 96. And 96 is the mean minus 2 standard deviations. So my mean in the middle going out in either direction means we are 2 standard deviations from the mean. If we're 2 standard deviations away, that means we sit in this 95% falling between 2 standard deviations. So we could say approximately 95% of 18-year-old women have a systolic blood pressure between 96 and 144 millimeters of mercury. Before I leave this page, Chebychev's theorem can be used for any data set, but the empirical or normal rule can only be used for normal or approximately normal distributions. So make sure if you're going to use the empirical rule, you know that data is normally distributed. If you don't know anything at all about the data other than the mean and the standard deviation, the only thing that we have is then Chebychev's theorem.